All right, this is chapter 5, section 10 on thick wall pressure vessels. A lot of slides, not a lot of meat to this one, honestly. It's just an equation, which again, I've said it over and over. You guys are very gifted at your ability to work with equations, so this should be fairly straightforward. The learning objective is the continuation of what we were doing working with thin and thick wall pressure vessels. We are now working with the thick wall pressure vessels. We're going to have a different set of assumptions, different approach, and we're going to come up with a different equation. It is that one, thick wall pressure vessels. We now actually have two stresses. Because these are thick, we now have a radial stress. That is, around across our cylinder, we're going to have a stress in the outer direction, not just, we had our hoop stress, which would have been along that curvature. And some of this I can help in class. I get to explain this with a scuba tank cylinder that I've got cut in half, but this is a little bit more challenging. But we've got a radial stress, which is outward through the thickness, tangential to the thickness or parallel to the thickness direction. And then that tangential, which is that hoop stress. And so there are two equations, and they're a little more complicated, and they are what they are. Let's see what we got with them, or where they came from. Let's figure out where they came from. So the first is a blurry picture, but we're going to start with that, and that we no longer can deal with just a very thin, and so you're seeing that we're starting to work with a row and a D row in our system. The row and the D row, that's really, row is, in this case, we're using row as the radius. And I think that's a little unfortunate, and I think some of the notation here makes this harder. I don't understand why that couldn't have been an R, but they went with a different route. So you're starting to see we've got, this is our generalized case, and so let's look at our nomenclature here. I've got an A, which is equal to my inside radius, and I've got a B. Where's my B? There it is. B is there. B is equal to my outside radius. And then I've got two other variables, pressure on the inside and pressure on the outside. So you could put a little tail on that, pressure on the inside. And PO, pressure outside. And those are going to change gradually across this R dimension. And so we're going to track that, and we wind up doing, I hate to say it, but we're going to wind up doing calculus. And the other thing is, because this is not thin, as I go out in d theta, as I go out in R, my d theta gets bigger. And so now we have to start taking that into account. So the next diagram that we get starts showing, yeah, you're right. Not only do I have an R plus dr, or a d, the stress has a stress plus a rate of change in the radial direction. I also am going to start seeing stuff changing in the tangential direction, and so those all come into play now, and so we wind up integrating it. So we get this little slice of element that we have to integrate our stresses over. And the stress on this side is an R, the stress in the R plus the change, the little tiny change of the stress in the R direction. And then I've got my dimensions on that little are a rho plus D rho, and then a D theta and a DL, because it's a three-dimensional stress cube. So this is like this is my thickness direction, and this is my width direction, and this is my length direction, to get this volume as I'm integrating this structure. I don't want to go through this, and I'll even give you one other reason why I'm not going to go through it, is because even with all this sophistication and the fact that we're going to do integrals and we're going to go wow, if you look in the book on page 258, it says, from a summation of forces we get, and then you're seeing what we were just kind of looking at there, that term, And then you get this, by neglecting higher order terms and noting for small angles. So that's making two different assumptions to eliminate terms that we don't want to deal with. This is not an exact answer. This is what we can work with. And so this is a better answer, but it's not the answer. It's what our human, fallible, limited minds can deal with. So that's where we are. And then we wind up getting this, and then you see it gets even better. Equation B cannot be integrated directly since they're both functions of the radial. So now this has just become a statistically indeterminate problem. And so then they wind up integrating between limits and using the stresses and strains. Fun stuff. And I've gone through the derivation, but again, it's not worth our time. It is not worth our time. If you're in grad school, this will be a great exercise for you. And I bet you spend 8 or 10 hours on it. But for what we're doing, no, we're going to jump ahead. We get these equations. These are the equations for the thick wall pressure vessels. The thick wall pressure vessel has two equations. One, that is the radial stress, and two, the tangential stress. Now, I want to make sure those are clear. It's now a thick wall. It's now a thick wall. And so I've got a stress in this direction, and I've got a stress in this direction. Now, what we know, this tangential, we're calling this the tangential stress, and that's not equal to, but it's kind of like, it's very much like what we were calling the hoop stress before. This radial stress, we didn't have that at all. We did not have a radial stress. And there's still a third stress. If you remember, we had an axial stress, and that axial stress is going to be in and out of the page. So I'll draw that as that little circle and a plus. That's the axial stress. That hasn't changed, actually. That was a very good solution. So that stays intact. Now, this equation has a lot of capability in it, and maybe we ought to spend a little time looking at the terms, but we already did in one sense. This radial stress is equal to a function of, and then I just want to take a second to go through the variables here. I've got that A, and that is my inside radius. And then my next one, I'll change colors, is B, and that is my outside radius. And then I'm going to a blue, and I've got my pressure on the inside. And I go with the dark navy, and I've got my pressure on the outside. Now those are the four variables, and we can start going through and going, yeah, that one I accounted for. That's outside radius, inside radius, outside radius, pressure, outside, inside. What's rho? What's rho? Rho is equal to the radius. That is the radial stress as I draw this out here. The stress in the R direction is a function of, and I'm going to write it out, the radius, which they're referring to as rho. And so you see that, and the tangential stress is too. The tangential stress is also a function of the radius. So it's a function of all these things. But then once you've done that, this term has the radius in it also. So you have to take that into account. Now, if you want to know where the worst stress is, well, the worst stress, let's go on to the next slide. We'll start with a clean slide and show you. So we want to look at where this is the worst case. Well, honestly, I can't do that. that easily for all situations. And the reason I can't is because if the pressure on the inside is greater, I know that B is always greater than A. So I can look at this term here and know that's always positive. And B is always greater, so that, but I need to know what my pressures are in order to figure out whether this term is positive or negative, and then have to look at that term, know whether it's positive or negative, and whether I want to add or subtract it. But you're going to be able to see that's going to be the worst case at either the inside edge or the outside edge. It's not going to be the worst case in the middle. So maybe that's all we can take away from this equation at this time. But now we're going to look at three special cases of how we use these equations. We don't typically use these in a generalized way. We typically use these for three specialized cases. So our first special case is internal pressure only, and that we're going to start with the equations for the thick wall pressure vessels, and then we're going to just simply eliminate the pressure on the outside goes away. So you can see I've got a squared pi minus a squared b squared pi. Well, some of that kind of ties together, and then that's divided by rho. Well, we just simplify that, and I'm going to simplify the bottom the same way. Those equations are going to take on this new structure, and now it's simplified, but we could get there. I haven't even provided, these are not on the study guide, because you can get to that by just working through this equation. You can see how that's 1 a squared. This is going to be an a squared pi over b squared minus a squared. That you get one of those, and then I multiply that by a b squared over rho squared, and that works out. Yep, it's not on the study guide, but that's one of our special cases. Our other special case, next special case, external pressure only. In that case, the pressure on the inside goes away, and this is going to simplify pretty much the same way. The answer is going to look like, there you go. And you know the warning I'm going to give you, it's not on the study guide. All right. Now, there you go. Third case, a solid cylinder. This really isn't a pressure vessel. This is just pressure acting on something, acting on a cylinder. And we get this, in this case, A goes away, and the pressure on the inside goes away too. Both of them go away. Well, if that goes to 0, it doesn't matter what pressure on the inside goes away, because that whole term went to 0. And this whole term, a squared here, that goes to 0. So this whole thing goes away. That makes this a lot easier. You can even see, I don't even need the second slide, over P of the outside divided by B squared minus A squared. And drum roll. Oh, could I have simplified it more? I guess I could have. Wow, look at that. I'm going to have to go back and check. Yeah, I guess I could have gone a little simpler because I had an A there that I didn't need, and then my B squareds would have canceled. So yes, those are simple. So a side note, and that is there's an equation 511, and this is before we get to the special terms. And in order to get these equations, remember there was this little thing I said, this becomes statically indeterminate. So they had to come up with our displacement equations. And so the displacement equation is available, and it's a function of the radial stress and the tangential stress. And so you have to take that big equation and substitute in, and then do a lot of algebra to get back to your displacements. But that can be done. And for each of the special cases, they have calculated, or they have done the algebra so that you can look at that and you can use those equations. Barring the derivation, you have a very good, you guys are very good at equations. So now you know what they are. You can go look them up and apply them as you need, and you'll be a master at the thick wall pressure vessel. I will start this with an example, because I think while these equations can be a little daunting and the row shows up and it really means a radius, you want to see one example. So we'll do example 519, and then you guys will be masters of the thick wall pressure vessel. So you can see the problem we're going to look at. That's a thick wall. That's a 4-inch thick cylinder. That's kind of amazing. But there you go. That's what's next. Don't worry, there's more coming. Oh, I got to turn off this.